Something happened beneath the Alps in 2026 that the world's most powerful scientific institution has not fully explained. Not a rumor, not a theory floated in an academic paper. An actual event, flagged, logged, and quietly set aside by an artificial intelligence that was built for one specific purpose: to find the things that should not exist. And it found something. Deep inside the 17-mile ring of superconducting magnets, buried 100 meters below the Swiss-French border, the Large Hadron Collider completed its most ambitious run yet. Run 3 had already rewritten textbooks. Run 4 pushed the machine to energies that would have seemed like science fiction a decade ago. But this 2026 configuration was different. The beams were tighter, the detectors were more sensitive, and the artificial intelligence monitoring the collision data had been retrained on every anomaly ever recorded, every ghost signal, every unexplained fluctuation from every run. Prior, it was designed to be unimpressed. It had seen everything physics could produce, until it hadn't. To understand what happened, you have to understand what CERN is really doing when those beams collide. Most people picture it as a kind of subatomic demolition derby. Smash particles together hard enough and see what flies out. But the real work is in the accounting. Every collision is a transaction. Energy goes in, particles come out, and the fundamental law that governs all of physics, the conservation of energy, demands that the books always balance. Every joule of energy that enters the collision zone must be accounted for in what emerges from it. Momentum going in one direction must be matched by momentum going in the opposite direction. The universe keeps perfect records. This is not negotiable. It is not a guideline. It is the bedrock upon which every equation in the standard model stands. So, when CERN's anomaly detection system, a deep learning architecture trained on over 15 years of collision data, began flagging events where the books did not balance, the engineers assumed it was a calibration error, a sensor malfunction, maybe a software bug introduced in the latest update. They checked. Then they checked again. The sensors were fine. The software was clean. The calibration was perfect. The books still did not balance. What the system flagged was something physicists call missing transverse momentum. The name sounds technical, almost mundane, but strip away the jargon and the meaning becomes extraordinary. Transverse momentum is the sideways kick that particles receive after a collision, the leftover push that sends debris flying outward from the point of impact. In a perfectly behaved collision, if you add up all the transverse momentum from every particle that flies out, the sum should equal zero. Equal and opposite. Newton's third law playing out at the quantum scale. But in these flagged events, the sum was not zero. There was a deficit, a gap, a direction in which momentum had gone, and nothing had come out to account for it. In the language of particle physics, this means something left the detector without being seen. And in the hypersensitive environment of the Large Hadron Collider, surrounded by layers upon layers of detection equipment designed to catch particles that exist for less than a trillionth of a second, something not being seen is not a small thing. It is a crisis. The question the artificial intelligence could not answer, and the question that has haunted the physics community ever since, is this: where did it go? Missing transverse momentum is not new. Physicists have seen it before, and they have explanations for it. Neutrinos, for instance, are famously invisible to detectors. They are electrically neutral, interact almost not at all with ordinary matter, and pass through the entire planet Earth as though it were made of smoke. When neutrinos escape a collision, they take momentum with them, and the books appear unbalanced until you account for them. But here is the problem with the 2026 anomaly. The physicists did account for the neutrinos. They accounted for everything they knew about. They ran every known particle through every known interaction and modeled what the momentum deficit should look like if only familiar physics were at play. The deficit that remained after all of that, the unexplained remainder, was too large, too consistent, too structured to be noise. It had a shape, a directionality. It pointed somewhere. And that is the detail that made the artificial intelligence flag it not once, not 10 times, but across thousands of separate collision events distributed throughout the run. This was not a single glitch in the data. This was a pattern, quiet, repeating, and utterly inexplicable under the current standard model of particle physics. The phrase that has begun circulating in the corridors of particle physics, spoken carefully, almost reluctantly, by people who understand the weight of the words, is mass bleeding. It is not an official CERN term. You will not find it in a press release or a peer-reviewed paper, at least not yet. But it captures viscerally what the data seems to suggest. Mass and energy, which are, as Einstein showed, two faces of the same coin, appear to be escaping the collision zone and vanishing without a trace, bleeding out of the experiment, leaving the known universe, if the most radical interpretation of the data is to be believed, through some kind of aperture or channel that our instruments cannot see. Think about what that means for a moment, not metaphorically, literally. If mass can bleed out of a collision event and go somewhere our detectors cannot reach, then there exists a somewhere that is adjacent to our reality, close enough to pull matter and energy into it, but fundamentally disconnected from the fabric of space and time that we inhabit. A layer of the universe that sits just beneath the visible one, a dimension that our instruments cannot probe because the things that enter it cease to interact with the forces that make detection possible. This is not science fiction. This is the theoretical framework that some of the most rigorous minds in physics have been developing for decades. It has a name, it has mathematics behind it, and for the first time in history, it may have experimental evidence. The theory of extra dimensions did not begin with CERN. It began with the uncomfortable realization that gravity is, by every measure, absurdly weak compared to the other fundamental forces of nature. The electromagnetic force, the strong nuclear force, the weak nuclear force. These operate at scales that make sense relative to each other. But gravity is so feeble that a small magnet can hold a paperclip against the full gravitational pull of the entire planet Earth. Why? Why is gravity so much weaker than everything else? One answer, proposed by physicists Nima Arkani-Hamed, Savas Dimopoulos, and Jihad Vali in the late 1990s, is that gravity is not actually weak. It is diluted. It is spreading itself across more dimensions than the 3 spatial dimensions we can see. While the other fundamental forces are confined to our 3-dimensional slice of reality, gravity leaks, spreads out, into extra dimensions that are curled up too small for us to directly perceive. If that is true, then particles produced at high enough energies might also briefly access those extra dimensions. They might slip sideways, out of our 3-dimensional space, carrying their momentum and energy with them, and vanish from our detectors as completely as if they had never existed. Missing transverse momentum, mass bleeding. The same phenomenon described from 2 different directions. And now, buried in the data from CERN's 2026 run, there may be evidence that this is not just a theoretical possibility. It may be happening right now. Under a mountain in Switzerland, thousands of times per second, something is slipping through a crack in the known universe. But here is what makes this story more than a physics lecture. Here is where the mystery deepens into something that feels almost conspiratorial. Not because anyone is hiding the truth maliciously, but because the truth, if it is what it appears to be, is simply too large to announce casually. CERN has said nothing. Since the anomaly detection system began flagging these events, there has been no press conference, no paper submitted to a journal, no carefully worded statement from the Director General's office acknowledging that something unusual has been observed. The institution that brought the world the Higgs boson, that held a global press conference for a particle whose existence had been theorized for 45 years, has maintained a silence about this 2026 anomaly that some observers are beginning to describe as deliberate. Now, to be fair, science moves slowly. Data from a particle accelerator must be cleaned, verified, reanalyzed, cross-checked, and debated before any conclusion can be responsibly announced. The process of confirming even a modest discovery takes months. A discovery of this magnitude could take years. What looks like silence from the outside may be, from the inside, the most rigorous data analysis in the history of physics. But the silence has a texture to it, a quality. When CERN found unexpected excess events in their data that eventually led to the Higgs boson discovery, physicists were leaking preliminary results to physics blogs within weeks. The culture of particle physics is one of enthusiastic, sometimes chaotic openness. Preprints appear on servers before peer review. Rumors circulate at conferences. The community is porous. This time, the porousness has dried up. The people who know are not talking, and the people who want to talk do not seem to know enough to say anything definitive. That silence, in its own way, is evidence of something, of how seriously the people inside that mountain are taking what they have found. Consider the alternative possibilities, because a responsible examination of this anomaly demands that we not leap to the most dramatic conclusion first. Missing transverse momentum has mundane explanations. Detector inefficiencies can mimic missing momentum. If a particle flies out at too low an angle and misses the detection equipment, its momentum disappears from the accounting without any exotic physics being required. Software errors in the reconstruction algorithms can create phantom deficits, beam-related backgrounds, stray particles from the accelerator itself rather than the collision, can inject spurious signals into the data. CERN's team has spent months eliminating these possibilities. The anomaly detection artificial intelligence was specifically architected to recognize and subtract all of these known sources of fake, missing momentum. The thousands of flagged events that remain after that subtraction are the ones that do not fit any known systematic error. Could it be dark matter? That is perhaps the least radical of the exotic explanations, and it has been seriously discussed. Dark matter, the invisible substance that accounts for roughly 27% of all the energy in the universe, has never been directly detected. We know it exists because of its gravitational influence on galaxies. But every attempt to catch it in a detector has come up empty. If the collisions at CERN are producing dark matter particles, new, heavy, invisible particles that carry momentum out of the detector and into the void, the signature would look almost exactly like what has been described. This would already be one of the greatest discoveries in the history of science. But some of the theoretical physicists who have been shown the data, quietly, informally, in the way that sensitive results circulate before they are published, are saying the pattern does not fit a dark matter signature cleanly either. The directionality is wrong. The energy distribution across events does not match the expected profile of any proposed dark matter candidate, which leaves something stranger, something for which there is currently no clean theoretical template. What if the gap in the accounting is not a particle at all? What if it is a geometry? In the framework of extra-dimensional theories, the missing momentum does not have to be carried away by a particle that we simply cannot detect. It could be carried away by the distortion of space itself, by a quantum fluctuation in the fabric of space-time that, at collision energies high enough, opens a temporary channel into a dimension that does not interact with any of our four fundamental forces. Not a particle, a doorway, one that opens for a fraction of a second, swallows a fragment of the collision's energy, and closes again before any instrument can resolve it. Thousands of times per second, consistent, structured, as regular as breathing. If this is what is happening, and to be clear, it remains a hypothesis, not a confirmed conclusion, then CERN has not just detected a new particle or confirmed a theoretical prediction. It has detected a physical feature of the universe that lies entirely outside the architecture of our current understanding. A hole in reality in the most literal sense that language can accommodate, and the mass is bleeding through it. The implications spiral outward in directions that are genuinely difficult to think about clearly. If extra dimensions are physically accessible at these energies, even briefly, then the universe is structured in a way that is fundamentally different from everything our physics has assumed. The three spatial dimensions we perceive are not the whole of space. They are a surface, a membrane. And whatever lies beyond that membrane is not empty. It interacts, it pulls, it accepts mass and energy that we pour into it and gives nothing back that we can see. And if we are pouring energy into it through a particle accelerator, the question that no one is saying out loud but everyone is thinking is obvious. Is anything coming the other way? In the theoretical literature on extra dimensions and brain-world cosmology, the framework in which our universe is a three-dimensional membrane floating in a higher dimensional space, there is no particular reason to assume the flow would be one-directional. The same geometry that allows our particles to slip into the extra dimensions might, under the right conditions, allow whatever exists in those dimensions to slip into ours. We do not know what exists in those dimensions. We do not know if the word exists even applies in the usual sense. We do not know if the laws of physics that govern those spaces bear any resemblance to the laws that govern ours. We only know that something is going somewhere that we cannot see, and the door appears to be open. There is a version of this story that ends with a prosaic explanation, a systematic error that took 18 months to identify, a beam background that was more subtle than expected, a software artifact that fooled even the most sophisticated anomaly detection system ever built. Science has been here before. The faster-than-light neutrino result from 2011 turned out to be a loose cable. The gravitational wave signal that caused brief excitement in 2015 was an instrumental artifact. The history of physics is littered with anomalies that turned out to be mistakes. CERN knows this better than anyone, which is why they are not talking until they are certain. But there is another version of this story, one in which the careful, methodical, exhaustive elimination of mundane explanations leaves standing something that cannot be explained by anything in our current toolkit. One in which the pattern in the data is not an error, but a signal. One in which the universe has been trying, through the medium of missing transverse momentum in a particle accelerator beneath the Alps, to tell us something about its own architecture that we did not know how to hear until now. And if that version is the true one, if CERN has genuinely detected a physical hole in the fabric of our reality, a point at which mass bleeds through the membrane of our three-dimensional space into some adjacent structure that we have never seen and do not yet have the language to describe, then what comes next is not just a press conference or a Nobel Prize. It is a renegotiation of everything. Every civilization has had its moment where the model of reality it inherited turned out to be insufficient. The Earth was not flat. The sun did not orbit the Earth. Time was not absolute. Space was not empty. Matter was not solid. Each of these revelations did not merely add a fact to the ledger of human knowledge. They dissolved a framework and forced the construction of a new one, and with each new framework came capabilities that the old one could not even conceptualize. We did not invent the transistor by improving the steam engine. We invented it by understanding quantum mechanics, a framework that the previous generation of physicists considered too strange to be real. What capabilities might become conceivable If the framework of extra dimensions is confirmed? If we learn to probe, measure, and ultimately understand what lies beyond the membrane of our observable universe? If the bleeding of mass turns out to be not a catastrophic rupture, but a door, one that can be studied, characterized, and perhaps eventually navigated? These are not questions with answers today. They are questions that the data from CERN's 2026 run may have made necessary to ask. The Large Hadron Collider was built to find things that should not be possible. It found the Higgs boson, the particle that gives all other particles their mass, the final piece of a 50-year-old theoretical puzzle. That discovery alone justified every euro and every hour of labor invested in the machine. But the physicists who designed it always knew that the Higgs boson was not the end. It was a threshold. The standard model, complete as it now appears, is manifestly insufficient. It says nothing about dark matter, nothing about dark energy, nothing about why gravity is so weak, nothing about the asymmetry between matter and antimatter that allowed our universe to exist at all, rather than annihilating itself at the moment of creation. The standard model is a map of a small room in an enormous building, and the walls of that room, it now appears, may have holes in them. Something is on the other side. CERN's anomaly detection system has put its finger on one of those holes and said quietly, without fanfare, without a press conference, here, right here. This is where the known universe ends. The question the world will be asking, when CERN finally speaks, when the paper finally appears, when the result is finally confirmed to a level of certainty that the institution is willing to stake its reputation on, is not just what this means for physics. It is what this means for us, for the way we understand our place in the cosmos, for the kind of universe we have been living in unknowingly, for the entirety of human history. Are we on the surface of a membrane in a higher dimensional space, with dimensions pressed up against us that we have never perceived and never thought to look for? Is the dark matter that constitutes most of the matter in the universe actually ordinary matter living in an adjacent dimension, visible to us only through the gravitational force that leaks between brains the way gravity leaks between extra dimensions in the theoretical models? Is the darkness we see when we look at the night sky not empty space, but something more like a wall, a surface beyond which reality continues in forms we cannot yet imagine? What if CERN is not just looking at particles, but peering through the only crack we have ever managed to open in the structure of reality itself? Something left the detector in 2026, and it has not come back. The accounting is off. The books do not balance. And the most sophisticated artificial intelligence ever trained on particle physics data has looked at every mundane explanation it was taught to recognize and said, in the only language it has, this is something new. What that something is: a dark matter particle, a graviton leaking into extra dimensions, a quantum fluctuation in the geometry of space, a genuinely new category of physical phenomenon for which we do not yet have a name, remains for now unknown. But the hole is there, the mass is bleeding, and beneath a mountain in Switzerland, in a room full of people who understand exactly what they may be looking at, the silence continues. The world should be listening to that silence very carefully, because when it breaks, nothing will be the same.